Harsh is here. Okay, let me start. So in earlier lectures, we introduced a simple toy programming language. And you saw that we showed how to use logic to represent set of states as predicates, and how we could model the semantics or the behavior of a program using as formulas in logic. Specifically, we saw the transition system formalism to model behaviors of program, as well as the structure operational semantics, which in both those formalisms, the semantics of the behavior was of a program was treated as a set of execution traces starting from some state, which by state is a valuation for the variables in the program, and it ends in a state, okay, that the and the final state if it is a terminating program. In this lecture, we show how to formally reason about programs by introducing, by looking at a specific logic that has been designed for that, constructed for that purpose, called HoareLogic, named after the person who designed this logic, Hoare. And there we can see how we could reason, we could actually correctness can be constructed as proof in this logic. And the reason we want to study this logic is because when you the model checking and abstract interpretation methods can be in a way considered as automating some fragments of this logic to prove correctness of programs. Okay, so it's just a recall slide. So we call that the program semantics in structured operational semantics formalism was defined by recursively by attaching, by defining what the states, the transitions, the execution traces that it actually produced. So I'm just showing this slide just to jog your memory. Okay. So what we'll be doing is first introducing the notion of what it means, for programs to be correct, and then look at HoareLogic. So we've kind of seen already some aspects and some concepts that we'll be using here, since you're already working on CBMC. But once we do this in full modularity, you will see how CBMC can be considered as automating this logic. So this is a motherhood slide. So why proof? Okay, because we can, rather than, so one way to do is to enumerate each trace that belongs to the behavior of a program, and then you can check them. Instead, a proof, when you construct a proof, you can reason about multiple traces at once. Okay, so that's the advantage. And in order to do proofs, we have to construct a proof system, which really means that a set of inference rule, a deduction system. These are rules which can then be proofs in that proof system that can be organized as a tree of formulas in that logic. Once we do this, then as we saw, we could do soundness, argue whether the logic is sound or complete. And the same thing can be, that question can be asked for Hoare logic as well, once we introduce that. Now, just like programs are defined recursively using grammars, you can see that these proof rules will also be the inference rules that belong to this proof system will be defined inductively on the using the grammatical structure of programs. Okay, this is once again the simple toy programming language that we had introduced earlier, which is constructed starting from a set of variables, and then there's a way to construct expressions, and then once expressions are constructed, these are the commands that are that you can make programs using this basic commands and those constructs that compose smaller commands. Okay. So I will first introduce this notion. What does it mean? What do we mean when we say, even before we can start discussing about proving programs correct, what does it mean by proving correct? Okay, one way to do that, usually correctness of a program is defined relative to some specification, which is expected to capture its expected, which is supposed to capture its expected behavior. And this can be done by defining a post condition, that is, the set of states that are permissible for the program to be in once it terminates. Okay? And then you also define, as part of the specifications, preconditions, some constraints on your on the inputs. Okay? And that's how you may recall in CBMC the spec is done. So by using asserts, post condition is defined as asserts, and precondition is done using assumes, because they constrain the inputs. Of course, this is but one way of capturing the specification of programs, and that is one kind of property. This is usually suited for defining the specification of programs that usually terminate, that start in some set of states and then they terminate. Okay? But of course, these are not the only things that we may want to prove. So there could be lots of other kinds of programs, like non-terminating programs, concurrent programs, for which these kinds of the specification based on pre and post condition may not be suitable. Okay, then you may want to, because concurrent programs in general are non-terminating, in which case you can't be specifying post condition for them. Then you will have to, your properties will have to be something like, some condition always holds good, or if you're in a certain thing, eventually some other event will happen. So there are all kinds of other kinds of properties that are of interest for programs. And also there can be properties involving the resources consumed by your program. But for now, and as Hoare logic specifically is concerned, the one that we introduced in capturing the specification and proving correctness of programs that are intended to start in a certain state and terminate in a state which is captured by post conditions. Okay, so let's look at an example. So yeah, even before we can answer the question if this program is correct. Okay, so as I said, we need a post condition. which describes the set of states. When I say state here, I mean valuations for permissible valuations for that the program variables can take when the program terminates upon the exit at the exit point. So let's suppose we define that by defining a predicate on the by defining a condition that the values of the variables can take. So y, we expect that it to be x factorial. Okay. Now, when you execute this program, is this program correct related to this post condition? Anyone? Siddhant?
Yeah, I'm just thinking. Just 1 minute.
Or if you're thinking, then someone can answer right away. And leave. Or anybody can answer. So obviously this is doing, okay, in y you expect to end up having factorial of x, which is not a sign, but one of the variables. So it is doing initializing y to 1. You start with z is equal to 0. X could be any arbitrary value. That is the catch here, okay? And then you multiply as many times as
Yeah, I think this is false because it won't include x. It will only go till x minus 1, I think.
Z equals Z plus 1 covers that.
yeah,
Oh, yeah.
Z is equal to plus 1. Yeah.
Right.
Yeah, I think this is a bit of a trick question, okay? Because what would happen if x were
0?
Well, even for 0, it is okay because y is initialized to 1. If x is negative, okay, so if I'm assuming x is integer and x is negative, it may not be, okay? So if you assume that x is unsigned integer, then it is okay. But if x can be in any integer, then firstly, don't know how you define factorial on a non-negative number. So there will be some issue. So to be correct, so your precondition, if under the constraint that x is greater than or equal to 0, indeed this is correct. Okay, so that's the intuitive notion, okay, that we have. Okay, so if you start in any state that satisfies a given precondition, then when you execute and the program terminates, then you should end up, the state that you end up in should satisfy your post condition. Okay. Let's take another example. And this can be quite tricky. So this is
Sir, if it never terminates, does it satisfy? It doesn't satisfy the post condition, right?
Yeah, I think we will be okay. So here I'm saying, yeah. So that's a very relevant question. So we will see there are two ways of. So the correctness of program can be. That's why there are two notions of correctness in general. Okay, one is what is called partial correctness, and another one is called total correctness. Okay, so a partial correctness, you say that if it terminates at all, then the post condition has to satisfy. It does not concern itself. Termination is not part of the correctness, but if you want to make termination as part of the correctness, then usually it is called total correctness. The total correctness requires that for every state that satisfies your precondition, you expect the program to terminate and terminate in the post condition. Okay, so for now, we will assume that we are interested in partial correctness. Okay.
So for our case, it is correct.
Yeah. For our case, I mean, if it's partial correctness, we only care about when it terminates. Okay. I mean, if it terminates. Okay. In this case, it happens to terminate as well. Huh? For the precondition that x is greater than or equal to 0.
Okay.
I mean, here it terminates no matter what, even for integers. Okay. But now here is a thing where once again a loop. You start, n can be in the initial state, it can be any arbitrary value, and let's assume that n is a natural number, unsigned integer. So if n mod 2 is 0, that is, if it is even, then I divide by 2. Otherwise, I set n to n 3 times n plus 1.
This is the Collard's conjecture, right? You can't easily prove this. I mean, you can't prove it yet.
Prove what? Okay, now, I mean, I'm asking a limited. I'll ask a limited question, okay? So I think there are certain aspects of it for which it is not known, okay? I mean, that's thing. But, okay, suppose I give the post condition as n is equal to 1. Then is there a precondition for which, if it terminates, can you give a precondition for which this is correct? Okay, for which if it terminates, then n is equal to 1.
I guess like we don't need any precondition because the only way it terminates is n equal to 1.
The power of 2, perhaps?
Yeah, that's certainly, okay, okay. So who said power of 2? Okay.
Chandradeep.
Okay, certainly for power of 2, if n is a power of 2, n will be 1. Okay, if you keep on dividing, then when n becomes 1, you will exit the loop. Okay, certainly this post condition will hold it. Okay, because it does terminate for that case. Now somebody else said that there are situations for which it does terminate. Okay, there was another comment which said that it will not terminate. That is not true. Okay.
Oh no, sir. I said like it will terminate, but like it will only because of the loop. Like it will only terminate when n equal to 1.
No, but that's not true. Just now Chandradeep said that if it's n is power of 2, then it'll terminate and give n is equal to 1.
Yeah. So like I'm saying that the only case where it terminates is n equal to.
No, I'm not. My question is not about termination.
Oh no, sorry. I'm not phrasing this correctly. What I mean to say is that the loop exit condition is the loop only exits when n becomes 1, right?
Correct.
So I don't think we need any precondition. So because if it terminates, then n will certainly
but there are
become.
but there are, for example, there are cases for which it that's an interesting question. Okay, for example, when n is equal to 5, for example, okay, it does okay, so let's go one at a time. So I mean, maybe what you're saying is for all cases, whenever it terminates, n has to be 1. That's a good point. Okay, what you're saying. So what you're saying is you don't need any condition because you know that whenever it terminates, it can terminate only when n is equal to 1. Yeah.
Yes.
Therefore, you don't need the thing. But certainly what Chandradeep said is certainly also a permissible precondition.
Yes.
Okay?
Yes.
So I think the point that I'm making here is, so the question of whether this terminates or not is an open question. Okay, whether it certainly, when it terminates, n will be equal to 1. Okay, what exactly are the preconditions for which it actually terminates? That's a different thing. Okay, so whenever it terminates, certainly n is equal to 1. And what Chandradeep said, that if n is a power of 2, then certainly it terminates. Therefore, you can have that is so then you can get the question: what is the weakest precondition for which such a post condition? There can be several different assumptions under which the same post condition, the program can be correct with respect to the same post condition. That's another point that I wanted to make. Okay, so what Chandradeep said, that precondition is certainly a precondition for which this is correct. And there could be other weaker preconditions for which this terminates as well. Okay. So for example, for n is equal to 5, it does terminate, because for n is equal to 5, you execute the else part. So, and then you may set n to 16, okay, which is a power of 2, and then it terminates as well. So there are weaker conditions for which it does terminate. Therefore, the point I'm making is that there's this so you can have the same post condition. The program could be correct with respect to different preconditions, and among them you can define the kind of the weakest precondition. So the largest set of states, which captures all the states for which, if it terminates, then it'll satisfies this post condition, is something that is called the weakest precondition that can make this correct. There's this notion of weakest. Okay, I hope you guys understand what I mean by a condition, a condition being weaker than another condition. Okay, so if anyone is not familiar, they'll have to ask me. Okay, so a predicate which characterize a set of states, a predicate P1 is said to be weaker, stronger than P2 if P1 implies P2. Okay, so it's if P1 implies P2, then P1 is said to be stronger, because if it is stronger, then there are more states that P1. Fewer states that P1 satisfies. If P1 implies P2, there are fewer states for which P1 is true than P2. So
the strongest precondition for this program will be a proof for the Collatz conjecture.
No, are you saying what would be interesting for a given post condition is to find out the weakest precondition? Okay, so what Chandradeep gave, that n is a power of 2, was not the weakest. Okay, because there are more cases. Okay, more input values for which this terminates, and when it terminates, n will be equal to 1. Okay. For example, n is equal to 5. Therefore, one interesting question will be, what is the weakest precondition that satisfies this post condition for this program? So we can think about that. Okay, but the limited point I wanted to make was that there can be several different preconditions that we can actually say that this program is correct. So these notions is what we will be formalizing and describing a logic. Okay, the Hoare logic to prove this. Yeah.
Sir, like if we get the proof of its termination, then it will be a proof of collapse conjecture, right?
Yeah, I don't know what exactly that conjecture is. Okay, is the conjecture how exactly it is saying? I mean, can you state
Yeah.
the conjecture? So
Yeah,
because
the conjecture is like basically conjecture is like you will always get to one if you whatever is inside this.
no, but I'm asking a different question. Okay. Now the question is, oh, well, we don't know. Okay. The question is, will you always get to, for any n, does this always terminate? We don't know. Okay.
Yeah.
The other question is, for every n for which it, that you start out with, if it terminates, will it, if it terminates, yes, it'll always be n is equal to 1. Okay.
Yes. Yes.
If it terminates, it'll be 1. But now I'm asking the question, what are those states? What are the set of values of initial value of n? Okay. For which, if it terminates, okay, then it satisfies. Yeah. Okay.
Yeah.
So that question I don't know. Okay. So that will be then the weakest thing. Okay. Yeah. So, and also I don't know. I mean, whether it terminates for everything. Okay. Or it does not, terminate. Okay. So until you answer this question, you don't know what the weakest precondition is, isn't it? Yeah.
Yep.
Okay. So as I said, we have partial correctness and total correctness. The partial correctness considers itself that, it proves, it expresses the correctness of a program only if it is, termination is not relevant. If it terminates, then you want it to terminate. When it terminates, you expect the post condition to be true. Total correctness requires for every precondition for it to terminate as well. Okay. So, but as I said, we will be concerning ourselves, for this, for the time being, with partial correctness, and this logic will be for partial correctness.
So we haven't yet defined the formal definition of preconditions and post conditions, right?
Yeah, I think that I will define. Yeah. Yeah.
Okay.
In the next slide, just a few historical notes. So this whole subject of proving programs correct, and this notion of using pre and post condition to define partial and total correctness was proposed by this gentleman Floyd in 1967, and this logic was proposed by Hoare in 1969. But there were earlier than 1967, but these concepts of program, what it means to be, for a program to be correct, a lot of people have contributed. Okay, McCarthy, Perlis, and Vaughan, they all had defined, attempted different way of defining what it means for a program to be correct. And Hoare presented it as a full-fledged logic with a formal semantics and a set of inference rules. And that was the beginning of this program software verification as a research field. And all this automation and tools such as CBMC, the basis is very much lies in this Hoare logic. And that's why it's important to understand Hoare logic. Just like resolution is important to understand SAT solvers, okay, to understand program verification, it is important to understand Hoare logic, and that's what we'll be doing. Okay, so here is the kind of the formal definition. See, someone asked how to formalize. Okay, so this is kind of when I'm introducing Hoare logic. In any logic, as you already saw, we have to introduce the syntax for the logic. By syntax, what are the formulas for that, the atomic formulas for that logic. Okay, and Hoare triple is the atomic formula of Hoare logic. Okay, and this logic, Hoare logic, already uses, okay, it's a triple, okay, where written this way, where Q is a program, okay, a piece of program, a piece of code in the in that grammar for the programming language that we have defined. Okay, so that let's assume that that's the thing. So it can be any Q is a program, P is a formula in a logic. Okay, that describes the precondition, and we'll assume that it can be any predicate logic with some theories, okay, of interest for us. If the program manipulates only arithmetic, variables range over arithmetic and in integer arithmetic, then maybe P could be an SMT logic with the theory of numbers, okay? Or P can be, in general, some predicate logic with some theories that are of interest to us. And so is R, okay? So that's what I will do. So we are already seeing, okay? So Hoare logic, by definition, includes the first order predicate logic as well, because the atomic formula, which is a Hoare triple, has P and R, the precondition and the postcondition, which are formulas drawn from first order predicate logic. Q is a program constructed as per the grammar in the logic. Okay. And what does this mean? Okay. So so we already know what it means to say P is true and R is true. So here is the truth assignment for this atomic formula. That is the only new atomic formula that we have. So it means what exactly we kind of informally already introduced. Okay, if the program Q starts in a state, so P is any formula denoting a predicate that can contain any variables, okay, or variables that are that appear in the program Q. Okay, and when we say that when you start in Q is in a state that satisfies P, means it's in a state. By a state, I mean it's a valuation, assignment of values for the variables. Okay, that it should satisfy P. If you start in a valuation for the variables, that's what I mean by a state that satisfies P. And if Q eventually terminates, the program terminates on that input, then the final state, that is the output that it is produced, is guaranteed must satisfy the assertion or the post condition R. So more formally, this is what it means. For every X and Y, so where X is with this set of variables, Y is a set of variables. If X satisfies P, the P of X is true, and when you run Q, program Q on that input, and if it terminates, then producing the output Y. Yeah, see, this is an implication. That means if program Q terminates, then the output that it produces satisfies R, must satisfy R. Okay, so that's what it means. Therefore, if the program does not terminate, then this is vacuously true. That's why this is captures partial correctness. Or if you start in a state, or if you start in a state in which the precondition is false, then also it is vacuously true. Okay, so that's what this atomic formula. This is the only additional atomic formula that is in the logic of Hoare logic, the language of Hoare logic. Any questions?
So just to be sure, here termination doesn't include the error state, right?
Yeah, no. Then, yeah, that's a. So let's, for the time, see, even the way that we introduce the structural operation semantics, if you make error, see, the termination and terminating with an error, okay, are two separate things. Okay, if we introduce error states, okay, then we are capturing, then it means that it then what we assume is that it terminates with an error state. Okay, so we could say that error states are also some there are values as that is part of our domain. So if it terminates with an error, I consider it as having terminated. Okay.
Yeah. Okay.
Yeah. So then your predicates will have to deal with those special error objects as well, if you care to do it. Or you could say that you can also, yeah. So so your predicates can distinguish between error and non-error values. Okay.
Yeah.
Yeah. So if you want to say, oh, whenever it terminates, it always it does not give error, then your post condition will have to take care of that. Yeah.
Yeah.
Okay, so here are some examples. So here I want you to pay attention. So I will go around the class to ask these things. Okay. So that's why. So when we say Hoare triple, sometimes it's said to be true if this condition holds. Sometimes you use we also say Hoare triple is valid. Okay. And the reason we say it's valid is because, as you know, this is a for all quantification. Okay. So that's why when it is true, this means that it has to be true for all valuations that make this implication to be true. Okay. That's why we also say that either Hoare triple is true and also use the topology that it is valid. Okay. Suppose you have x is equal to x plus 1. So let's see how many people are here. So I'm going to go around. Everybody is here. Yes, so 6 people. Okay. Andrew is also here. So I'll go in order. Okay, Anli, is this Hoare triple valid as per the semantics?
Yes, it's valid.
Yeah, okay, because start with x is greater
We
than
start with 0.
Yeah, so then based on this semantics of assignment statement, okay, so this is true. Yeah, skip is, as you know, is a command that does nothing. So Chandradeep,
No,
why?
not there is no precondition about y.
Correct. Yeah. Okay. So y could be anything. So whereas here, so because we don't do any, yeah. So there's no guarantee that y can be greater than 0. Harsh.
Yes, sir. Just a second.
No, here this is a question. It's not a yes or no question. So I'm asking you, what is
Okay, what is the strongest possible?
the strongest thing that you can say after you?
If x greater than y, then x equal to y. The strongest thing Oh, okay. Yeah, you can say that y less than equal to x.
Less than or equal to, right? Yeah?
Yes, yes, yes.
X less than equal to Y,
X
right?
less than or equal to y,
Okay.
right?
Yeah,
Not
yeah.
1. Yeah.
Yeah.
Also, is it not possible to have more complicated terms on the right hand side, like, or rather expressions?
No, I'm just yeah. So that's the thing. Yes, you can have. When we actually, I'm just picking some examples. Yeah, you could certainly, as I have already shown you.
So the strongest condition would be if X greater than Y, then X is equal to Y, right?
No, but here I have the exact variable y. Okay. So it is because the right hand side you can have arbitrary expressions. Okay, but you can. I'm stating the thing in terms of y. I don't know what you mean by if you can have more complicated expressions.
So can we have the expression X greater than Y implies X equals Y, like the previous and later version? So there are some tools like F star where it's allowed to have like assign different variables, and then we can write the previous versions if the, X greater than Y, then for the next versions X equals Y. Is that possible here to write?
For example, I know what. No, I don't understand your question. Okay, so what is it that you can state that can make this thing true? Can you?
Yeah, sure. So what I'm trying to say is that the part in between the Q, it can be thought of as a function, right? Which has some initial variables X and Y and some final variables X prime and Y prime. It's possible. Is it possible to use this terminology and express precisely this fact that if X is greater than Y, then X prime is equal to Y prime? Is that
but
already there in this framework, or
you could make whatever precondition you want. Okay.
no, I'm saying just in the post condition have an implication.
No. But that's that comes as part of the proof. Okay. Now here I'm asked the question: what is it that you can state at the atomic level? Okay.
I
As
see.
Atomic.
We had R of Y. So Y is the output. So we can't use variable from the input.
One.
We had
Yes.
P of X and R of Y. So we can't use X in R of Y, right?
P of X is power of Y. I don't understand.
We had P of X produces Y on X.
What is P
of
here?
Y.
Huh?
That whole condition thing. P, Q, R triple.
Yeah. P is here true. Okay.
Yes. No, he is asking if we can use the X of input as the post condition output. But we had the post condition is R of Y.
No, but no. This is all stated relative to the precondition. You can make other preconditions if you want. I didn't exactly. So let's move on. I mean, I think I have answered his question. So let's move on. Okay. How about this? Okay, Dhruv. Yeah.
So if X greater than 0, what is a program we can give so that it's false, is it?
Yeah. For what program can this triple be?
X equals true.
Think about it. Okay. So this is like a bit of a tricky thing. So false can never be true, right? So no state can satisfy false. Okay.
It can if we have like a type error, right? That's why I said X equals.
No. Don't confuse with type error and so on. Okay. Type error these are runtime things. Okay. So I'm assuming that a program is syntactically correct. Okay. So don't, but even if there is even if error is an object, it doesn't even satisfy false. Okay. There can be no value. See, error will be, don't say, oh, if there is a syntax error, there's a type error. Okay. This is all runtime behavior that we are talking about. Okay. So if
type check is
the notion of error will also be a value, a distinguished value of my domain. Okay.
I'm a bit confused. So so we know that X is an integer because of the precondition. If the program asserts that X is
let's assume that X is, so that is true. That's a good point. So that I give you. So let's suppose X is integer. Okay, so it really doesn't matter for the thing. The most important thing is that the fact, maybe I'll answer in the interest of time myself. So if you see, false can never be, in no state can satisfy false.
Right.
Or if it terminates, whatever the value with it terminates, it can never satisfy the post condition. Therefore, in a way that this can only be satisfied if this program never halts, never terminates. Okay.
Right. Yeah.
That was the answer that I was expecting. Yeah.
So program terminating is not the same as program having an error, is it? Like
No,
not
I already answered that question. If program has a runtime error, it terminates with that error object. Okay.
Okay, I see. Okay.
And error is a distinguished value in my thing. Okay. Distinguished value in my domain. Okay. So I'm assuming my domain will be error, will have integers plus this weird object called error. Okay. And if there is a runtime error, okay, division by 0 or something, it'll return error. Okay. But a false is a predicate that cannot be true for any values, whether it is integers or error. Okay, that's how I interpret it. Okay. So I've already answered the question. So if it returns error, it is assumed to be terminated. Yeah.
Okay. Cool.
Okay, who have left? Siddhant?
Yeah, I think if no matter what you put in the post condition, this will always be valid.
Correct.
Because there are no, there is no valuation which satisfies the precondition.
Precondition. That's most importantly because it's an implication. The whole triple semantics is an implication. So false implies everything. So you can put any predicate you want, okay, including false, for which as your post condition. Okay. So so that's what it is. So specifically, for example, yeah. And how about this? Who I have missed? Sayag?
So you're asking whether this is valid, right?
Yeah. See, starting with true, okay? So skip does not do anything, okay? So true is, includes every state. Therefore, since skip does not do anything.
So this isn't valid, I would say.
Yeah, this is not valid. The post condition has to be true in this case as well, okay? Chandradeep? Oh,
Anything works.
going down to Anli. Started with an Anli. So this is.
Sir, I have a question first. The difference between 0.4 and 0.6 is that there is a case of non-termination in case 4, but not in case 6.
Yeah, because skip always terminates. Nah? So there I was asking you what program, okay? So since skip always terminates here,
Okay.
skip is a simple program, it always terminates. And therefore, since it terminates, it has to terminate in some state, okay?
Yeah.
Which can never satisfy false. That's why this is not valid, yeah?
Yes, sir.
Yeah, and to make valid this, since skip does not do, does not change anything, whatever the state here, it has to be returned, and therefore it must include every possible state. Okay. Yeah. So this here is, you don't care what your post condition says. Okay, I don't care anything. Any state I allow. Therefore, you can have this is valid for true. Okay. Yeah. So you can start with any state. Okay. Either it does not terminate, in which case any post condition is true. Or if it terminates, it doesn't matter what the thing is, and so on. So there are more examples that I have here. I will let you go through that yourself in your leisure time. So what I want to do now is to formally define, okay, as inference rules. So now these inference rules had to describe, had to specify when a Hoare triple given, is for all programs, and the way it does is you have an inference rule for every atomic commands in the programming language, and then you have assuming that for every construct in the language, composable construct, like you will have an inference rule that gives when a Hoare triple would be valid for that program that is constructed from subprograms. So we start with skip. So in these, as you will see, these inference rules are schema, okay, in the sense the post and the pre and the post can be any predicate. In our case, we assume that it is predicate logic with some theories that are of interest. So skip means if your precondition is any predicate P, since skip does not change, does nothing, it does not change the state, then you could say that the post condition P should be true as P should be true for that precondition. The strongest thing that you can say is this P. Okay, so that is thing. So this you could say, because it's a basic command. You start with knowing nothing about your component program. So similarly, okay. So let's look at the assignment rule. Okay. So here you have an assignment where X is assigned E, where E is an expression, arbitrary expression in the language, which can have other variables, any other program variables, including X in it. Okay. So when we define the semantics of these things, you already saw that you could either do it, semantics of these commands and these inference rules, you can do it in two ways. Okay. One is, given a P as a post condition, what is the weakest precondition that I can define for which this Hoare triple will be valid? That is one way of doing it. Okay, that is how I'm defining here. Okay, that's why. So if I start, if I want to, after executing this assignment statement, if I want to be in, if I want the state to satisfy post condition P, then what is the weakest thing that I should do? Since I know that X, this assignment statement will assign whatever the value of this expression to X. If specifically X has to satisfy P here, then it better be the case that P be true for that value, that expression evaluates prior to in the pre-state. Okay, that's how this thing is defined. So this notation P, this one says that in P, which is a formula which can have X, every instance of X has to be replaced by E. This is a substitution operation inside formula that I'm defining. Every instance of X in P has to be replaced by E, where E is the expression. Okay. And that's it. So, and the intuition is that if P has to hold good on the post value that X gets taken, since X is assigned whatever the value of E as per how it is evaluated in the before the execution of this thing. So P has to be true for the value that E evaluates to. Okay.
Sorry, this is like, how is this the weakest precondition? The weakest precondition should be that X could be anything, right? X can have any value.
Why? How? If X
Because
no,
because
X,
it
no, if X can have any value,
yeah, then after the statement X will always have E. So the post condition will be, I mean, yeah, isn't that true?
no. But let me give you an example. No. See how? No. If X can be of any value, what is the guarantee that P will be true? See here, I don't know what P is. If you're saying I can start with any state in which X can have any value, how do I know that after since in the post state X gets the value of E, how do I know that P will be satisfied? So that's why it better be the case that P, that whatever the value of E is in the pre-state, that E has to be true. So let me take an example, okay? Because I mean the way I'm saying is, if it is true, if the weakest precondition is true, why will it satisfy P? Okay, so let me take an example. So the example is here, and that will here it is, okay? If you want X to be greater than 0, if your post predicate is X is greater than 0, and your assignment is X is equal to X plus 1, so X plus 1, it's better the case. If X has to be greater than 0 here, then that's your P predicate, okay? So like what you said, if you start with an arbitrary state true, that cannot be the weak, because there's no way. If you start, if X can be willy-nilly any value, how can you say that X will satisfy P? So that's why if X greater than X has to be greater than 0, since I know that what is the value of X in this post state is whatever that X plus 1 evaluates to in my pre-state, therefore X plus 1 better be greater than 0, which is the expression, okay, that is assigned. Okay, so I'm replacing whatever the expression into this predicate. I'm substituting every instance of the variable X in that formula that denotes P, in P with X plus 1 greater than 0. So that's why you get this. X has to be greater than or equal to 0 for it to satisfy X, to guarantee X is greater than 0. That's why this way of applying backwards is the weakest thing in order relative to that P, okay, that you have. Yeah. Does that answer your question? Hello? Yeah. Any questions there? So can I move on?
Siddhant dropped out, did he?
Oh, I see. Okay. So if not, and nobody else has any question, then I will move on. Yeah, I guess we have one fewer participant. Okay. So there's also a forward way of expressing this. Okay. Given a P, a condition, yeah. So anyway, so I was asking, yeah. So so let me move on. Okay. So if he still has doubts, he can ask the question. So another way to define is in terms of by specifying the strongest post condition. So if you start with some predicate P, then you have this assignment X, for E, where you have, some expression which can involve the variable X also. Post condition, usually, people use the weakest precondition formalism because there you could get the weakest condition by simple substitution, whereas for the strongest post condition, the condition is a little bit more complicated, although it can be simplified also. So you have to make sure that so there exists a value such that P is true. That if P is not satisfiable at all, like it's false, then it will be false. In the post condition, you could simply say that X is just I'm sorry, no, this should just be, there exists this parenthesis should come here, okay? So it should go all the way till the end. So there exists we have to make sure that P is true, that there exists at least some value, okay? And then X will be equal to, whatever the value that you get executed by X will get the that value, okay, for which P is true. So more distinctly, without existing quantification, it can be stated this way: if P of X is true in the pre-state, it's a precondition, then if E is equal to, then what it means is that we can introduce some constant X naught. Okay, it can be an arbitrary constant. So, and that which is whatever the value that X has in the precondition. Okay, and then I can substitute in E every instance of X by that arbitrary constant, and that's what X will be. Okay, that's what this part is stating. Okay, and then P of X naught has to be true. So it's that's how you have. So that's why it accounts for the possibility that if it is false, then your strongest post condition itself has to be false. Okay, but otherwise it is whatever the initial value. X naught denotes an arbitrary constant that which satisfies P. Okay. Which does not appear anyway. This could be considered as a new variable that can take out any value that does not exist. It's not among the variables used in your program, or you can view it as an arbitrary constant. Okay, that's what this thing says. Okay, so in your post condition, the strongest thing you can say is X itself takes the value that you get by evaluating the expression, the right-hand side expression, for whatever the value, that is there in whatever the value of X is in the initial state. And that's all this thing is saying. And this P of X naught is added, to ensure that if there is nothing that satisfies P, then you will have you will have the post condition to be false. Okay. So let me take an example of this. Yeah, so here you can see this. So I hope the font is big enough. Yeah, so this is how it can be used, okay? P of x if you have x. So for example, I'm taking the same example with x greater than or equal to 0 as the precondition here. And I do x is equal to x plus 1. And I'm going to be deriving the post condition using the forward version of the assignment rule. So what that says is, now for p, what we have for p is x greater than or equal to 0. So I'm saying if x has some value x naught in the pre-state, then x naught has to be greater than or equal to 0, because that's what the precondition states. And the value of x in the post state is x naught plus 1. Now this satisfies x greater than 0. Why? Because x naught greater than or equal to 0 and x is equal to x naught plus 1 means x must be greater than 0, because x naught is greater than or equal to 0, and I'm the post condition says that x must be x naught plus 1. So you see, the two things are equal. So you could either do it this way or the other way. Okay. Okay, now I will end by showing you. Yeah, now we are. Yeah, that's what this thing is. Okay, so sequential composition. Okay, so now if you have your program as being constructed out of two smaller programs by using the sequential composition operator, then you will have to have an inference rule with some preconditions, so that if I start with the precondition P and after executing Q, I end up in a post state described by R. And then if I start with any state that satisfies R, and then when I execute S and terminate, I satisfy the T condition, then when then the result of executing the program, which is the sequential composition of these two things, will is guaranteed to satisfy this triple, which says that if I start with P, then when I execute the program, which is the composition of these two states, these two sub-programs will I'll get will satisfy T. Okay, which is just the way that which captures the meaning of sequential composition. Okay, this I will. Yeah, I will come to this later on. Okay. So now, what should be an if-then-else for if-then-else? Okay, this is a forward way of this is a forward kind of rule for capturing the effect, capturing the semantics of an if-then-else command. Okay, as in terms of a Hoare triple. So if I have if-then-else, if I execute intuitively, if I start with the precondition, a state, a pre-state which satisfies P, then what happens? Okay, that if P is, if the state satisfies is such that B, the condition is true, then I execute Q. Otherwise, if P, if a state that satisfies P is such that B is false, then I execute this, and that's what is captured. If I'm in a state P, that is what the assumptions about the horizontal line in inference rule are captured. Assuming that I'm in a state which satisfies P, and if B is true, then when I execute Q, R is true. Then if the state which satisfies P is such that not B is true, then when I execute X, R happens to be true. Under these two conditions, then I can be it's guaranteed that if I execute this if then else statement composite command, then if I start with P, then R will be true. Okay, then I'm at the in the post. That's because in any state that satisfies P, either B has to be true or not B has to be true. If B is true, then the post condition will be as per what the execution of Q, and the other case as per the execution of S, and that's what. So if R happens to be, then I can do. So similarly, so yeah, so this will be the last slide. I'll be done. So if yeah, there is a backward way of doing it as well. If I see here, I'm defining the thing in terms of starting with P. So here I can also do by starting with a post condition R. Then if I executed, if the weakest precondition for executing C2 is Q, and weakest precondition after executing C1 is P, then the weakest precondition from which I can start to guarantee that R is that it is the disjunction of these two things. Okay, so I know that I will, I'll show some examples to convince these things. So I'm going to have to stop here because I'm hitting the thing. So it can be described either this way or this way. So this one is useful when you want to do proofs in a forward direction, which I will illustrate in the next class, or you can use this version, the second version of the thing, when you want to do backward proofs. Okay, so yeah, so I'll stop here and reserve your questions until next time. Please, I'll upload these slides, review them, and if you have any questions, let's visit them on Friday. Okay. This one, I don't think I'll be, on Wednesday, by the way, I want, on demand, you can, Diganta, you ready for a tutorial on Thursday, I mean, okay?
Yeah, I can take next week. Wait, sir.
No, wait a minute. Today is Friday, okay? So, no, I'm getting ahead of myself. Okay, so review the slides and have your questions, and any questions that you might have. I'll go through more examples, with these inference rules, to illustrate these inference rules on Tuesday. Okay, I know Monday your assignments are due. Okay, and I hope I expect to give out an assignment by next class, and maybe that can be the subject of topic for the tutorial class on Thursday. So I'll see you Tuesday. Okay. Thank you.